Welcome back to the course on audio signal processing for music applications. Until now, we have seen how to compute the spectrum of a signal, it's STFT, but real sounds cannot be represented by a single spectrum. Sounds change in time, and we need to capture this time variation. The short-time Fourier transform is our solution. Again, this lecture is divided into two parts, so this is the first one. We will first present and explain the short-time Fourier transform equation and then discuss what we call the analysis window. This is the short-time Fourier transform equation, basically a modified version of the DFT with few very important differences. So for example, the input to the equation, the input signal, is not just x of n, but is the multiplication of W, which is our analysis window, by a fragment of x of n. Okay, so here x is has an argument that has n, our time index, but also has a frame number and a hop size. So L is the frame number, and this is our time index. So we will be iterating over L. So we will be skipping through time this way, and capital H is our hop size, how much we're going to hop from one time instances to the next. So basically X is going to be changing in time according to L and H, and then at every time instance, at every L, it's going to be multiplied by this analysis window W of n. The rest is the DFT. So the only thing that changes is that the input signal changes, and therefore the output also is not a single spectrum, but a sequence of spectra. There is the x sub L, so the variable L is the frame number, so that means that the output of the short-time Fourier transform is going to be a sequence of spectra, each one of the same size and having magnitude and phase, but each one differently because the input will be a different fragment of the sound, stepping through the sound in a progressive manner. Okay? So to emphasize the idea of zero-phase windowing that we already have talked about, from now on we generally specify the time index to go from minus n over 2 to n over 2 minus 1. Okay, so it's always centered around 0. We don't have any phase changes. We don't have any kind of shifting in the time and therefore in the spectrum. The windowing is a way to step through the sound, as I mentioned. So here we can see a depiction of that. And if we use the analogy of image and video, we could relate a spectrum with a photograph, a static image, and then the short-time Fourier transform with video, a time-varying image. So here we see in this picture the whole time for a sound at the bottom, and how we are basically stepping through the sound by windowing the sound with this analysis window, and therefore being able to get all the sound as a sum of basically sound fragments. Okay, to better understand the effect of windowing a sound, let's put an example of what happens when we window a real sinusoid and then compute its spectrum. So if we start from a real sinusoid, we already have seen that. So it's a cosine with a frequency index k sub 0 and an amplitude a sub 0, which can be expressed as the sum of two complex sinusoids, one with a positive frequency, another with a negative frequency. Then if we substitute into the short-time Fourier transform equation this signal and we window it, we can step through these different steps in which we first put x of n in the equation, then we are substituting by the sum of these two complex exponentials. Therefore, because of the linearity of the DFT, we can split these into two equal equations in which in each one we have a complex exponential as the input signal, and the amplitudes can be moved outside, and basically what we get back to is the sum of two DFTs of the window and with a frequency shifting operation. So basically at the end here we see that the result is the spectrum of the window, of course frequency shifted by this the frequency of the input signal, and multiplied by the amplitude, by half of the amplitude of the input signal, plus of course the other window at the other complex exponential frequency. One is the minus frequency and the other is the plus frequency. So this will be the result of this cosine, so which is basically the transform of the window shifted to the frequency of the input signal and multiplied by the amplitude of the input signal. And with these plots we can understand this windowing process a little bit better. So on the top we have the window, and underneath is the windowed sinusoid that we have as our input signal, and then the transform of the window can be shown on the top, in which the transform of this window, which in this case is a Hanning window, is the magnitude spectrum centered around 0, okay, and with the symmetry and with the given phase. And now if we take the DFT of the windowed sinusoid, well, what we are seeing is basically the same shape than the window, but at the frequency of the sinusoid, the two frequencies of the sinusoid, the positive and the negative frequencies, and at the phase of the sinusoid too. So we have the two values for the two phases with this anti-symmetry that this analysis results into. Okay? So from this discussion we can realize the importance of the analysis window in the spectrum of a sinusoid, and thus of any sound. It's clear that we have to spend some time explaining the windows. So an analysis window is generally a real function and is symmetric around the origin, and this is the simplest window, the rectangular window. Its time domain is nothing too particular, but its magnitude spectrum is much more interesting. So time domain, it just has value of 1 for the duration of the window, in this case 64, and the spectrum, the magnitude spectrum, has a shape which we call it is a sinc shape, because the transform is a sinc function, and it basically could be described in many different ways, but we focus on two main aspects: on what we call the main lobe, the peak at the center, and we'll be talking about the width of the main lobe mainly, and then we talk about the side lobes, which are these small lobes next to it, and we basically focus on the level of the highest of these side lobes. So we will talking about the highest side lobe level. Okay, so there are many windows used in audio signal processing, and this is the list of windows available in the SciPy module of Python. So we can go through them, and we can see quite a variety of windows. Some of them we're not going to pay much attention to, but for example we will be talking about the Blackmon window, we'll be talking about the Hamming window, the Hanning window, we'll be talking about for example the triangular window, etc. Some others are not so much used in audio. Each window can be distinguished from the others by measuring the main lobe width and the side lobe level. And each window offers a different compromise with respect to these two values. So let's show some of them. So the first one is the rectangular window, and the equation shows how it's computed. And the spectrum is what we call a sinc function. Is the sine pi k, where k is the frequency index, divided by another sine function. So if we look in the plots, the spectrum could be thought is is the magnitude of spectrum, so it's the absolute value of this wk. So basically is a sine function with a kind of a attenuated function applied to them at the boundaries. So it results into this shape, very characteristic shape, that's going to be called this sinc function. And talking about how to describe it, we mentioned about the width of the main lobe, and this has two bins, and two bins means two samples. And this, we have to be careful because this is measured when the DFT is the same size than the window. So if we take a window size of the same size of the window, let's say 10 samples, then it's going to be 2 bins. But generally, since we do zero padding, then the number of bins is higher. But this is because of the zero padding. And we normally do it in order to better visualize the shape. So in fact, this shape has been generated by a lot of zero padding so that we can have this smooth visualization. But strictly speaking, the number of bins that we refer to is 2. And the side lobe level, the highest side lobe level, is minus 13.3 decibels. So the distance between the centered peak and the first side lobe level. Maybe the most popular window is the Hanning window, which is a raised cosine. So the equation is we do 0.5 plus 0.5 of the cosine, so this raises the cosine, so it's just one cycle of a cosine. And if we compute the spectrum, it also can be expressed as sums of the sinc functions. In fact, all the windows can be expressed in the time domain by sums of cosines, and in the frequency domain by sums of this sinc function. So in this case, is the sum in the frequency domain of 3 sinc functions. Okay, and again, the two values that characterize this shape, this frequency domain shape, is the width of the main lobe, which is 4 bins, so twice as much as the rectangular function, and the side lobe level is minus 31.5 decibels, so which is lower. Okay, now the main lobe is wider, and the side lobe level is lower. The Hamming window is very similar to the Hanning, but with a small and significant difference. It's a raised cosine with a step at the sides. By having these small steps into the sides, we get a magnitude spectrum that maintains the same main lobe width, so that's good. It doesn't get wider. But in exchange, we get a much lower side lobe level, minus 42.7 decibels. And this is, as we're going to see, an important thing. The ideal is to have the lowest side lobe level and the narrowest possible main lobe. So this is a good window. Of course, nothing comes for free, so the side lobe levels do not decrease so abruptly as they go away from the main lobe. The Blackman window is the sum of two sinusoids, and with that we accomplish a significant improvement in terms of the side lobe level measure. Okay, so we see the magnitude spectrum, which the main lobe is wider, is 6 bins, but the side lobe level is lower, is 58 decibels. And that's good because that's starting to be quite useful value at the side lobe level for many audio applications. So we will come back to that. And then finally, the window I want to end talking about is the Blackman-Harris window, which is a very special one. because we could basically say that it has no side lobes. So it's a sum of several cosines. In this case, it's 4 cosines with different coefficients in the summing. And then in the frequency domain, the magnitude spectrum, the main lobe again gets wider. In this case is 8 beams, but the side lobe level is minus 92 decibels. And if we think about it in terms of signal to noise ratio, which is a very important factor in digital signals, 92 decibels is basically below the noise floor of 16 bits of the kind of signals that we deal with. So basically that means that the side lobes, and if we consider them as artifacts or as noise, they are not heard. In other windows, we could say that these side lobes are artifacts that can be heard. Anyway, again, we will come back to that. And now to finish, let me just compare some of these windows being applied to the same sound. So we start with a fragment of a sound of a certain length, and we are applying 3 different windows. The first one is the rectangular, the next one Hamming, and finally the Blackman. Clearly very distinct spectra. And by looking at these, we can see kind of that maybe the best for this particular analysis is the Blackman. We see a smoother spectrum. We see these peaks much more clearly distinct. And in fact, these peaks correspond to the harmonics of the sound. Okay, so this is all, and there is a lot of references for the topics I covered, especially about windows. In Wikipedia, you can find quite a bit of information about the short time Fourier transform, about windows. Julius, in his website and his online books, discusses this quite a bit, so that's a very good reference. And that's the rest are the standard credits and references. So this is all for the first part of the lecture on the short time Fourier transform. We have explained the basic equation of the short time Fourier transform, and we have focused on the analysis window. In the second part, we will continue with this topic. So I will see you in next class.